Sorry, I think I fixed it. I think my mic was muted. Try this again. Jake here, coming at you with another math lesson, doing it live today. Today we're going to be going over some U-substitution problems and U-substitution method in general. I want to show you some tricks that should help make U-substitution a lot easier for you from beginning to end. So if that sounds good to you, be sure to stick around to the end of the video, and by the end you should be feeling a lot better about U-substitution problems and can go get some more practice on your own and really get it down a little bit more solid. But let's go ahead and jump on into the examples I got for you today. And this actually is one of the topics covered on my integral calculus cheat sheet or my Calculus 2 study guide. If you want to check that out, there is a link down in the description below. Also, the pinned comment contains that same link over to my website, so you can go check that out and get yourself a copy. It's available for instant download, so you can have that within a couple of minutes. And as always with these live streams, if you do have any questions along the way, please be sure to drop those in the live chat. I'm happy to help address whatever questions you have, even if it's not about U-substitution. That's what I'm going to be talking about. And if you have questions on that, obviously that's great. But if you got questions on something else that you're going over in your calculus class, feel free to drop those in the chat as well, and I'll do my best to answer those for you. So here's the first problem we're going to be going over. We are going to evaluate the integral by making the given substitution. So this is an interesting kind of example that you see actually pretty often when you're first learning U-substitution, where they actually will tell you, here's the substitution to make, now make it and use U-substitution to solve the problem. So in this case, they're telling us that the integral we're going to solve is dt over 1 minus 6t all to the fourth power. And then the substitution we're going to make is u equals 1 minus 6t. So with U-substitution, in general, the first step is kind of figuring out what the substitution you're going to make is. In this case, that's already been given. So that definitely does help alleviate the difficulty of U-substitution. The next example I'm going to be getting into in this live stream is going to be, I'm going to spend some more time talking about how to figure out what substitution to make, or how to make what to make your U. But for this example here, that's given. So really we can just kind of skip ahead to the actual substitution part of U-substitution problems. So when we're doing these U-substitution problems, once we've figured out what we want to make our U, or the thing that we're going to substitute out, the next step is to basically figure out what du is. So du you're going to figure out by just taking the derivative of whatever u is. So du, if u is 1 minus 6t, we're going to take the derivative with respect to t, because t is the variable in this integral equation. We know that because we have a dt right here. So as a result, we're taking the derivative with respect to t of u in order to find this. Well, the derivative of 1 of a constant is always going to be 0. And then the derivative of minus 6t is just going to be minus 6. And then when we take the derivative with respect to t in these U-substitution problems, we then need to add on a dt in here as well. So where this is going to come into play is, now what we want to do is we're going to rewrite our integral in terms of this u and du instead of having it in terms of t and dt. So to do that, what you want to do is first start by going to your integral and replacing whatever you've determined that your u is going to be with u. So in this case, you can see that we have 1 minus 6t right here, which is exactly what our u is. So what we're going to do is we're going to go to our integral, and we're going to replace what's in the parentheses here with u. So doing that is going to leave us with u to the fourth on the bottom here, on the denominator. Then what we need to do is deal with our dt here, because dt we also want to convert to be in terms of du. Well, to do that, what we can do, we kind of figured out this equation over here that involves dt. All we really have to do now is take this equation and solve it for dt. Well, to do that, we can just divide both sides of this by -6. And we get basically 1 over -1/6 times du equals dt. So dt is the same as negative 1/6 du. So we could basically think of doing negative 1/6 times du, replacing our dt here. So now once we've done that, there's a couple things to kind of point out right off the bat here. First of all, the numerator of this fraction is just a constant, negative 1/6 times this du. So whenever we have a constant, what we can do, well, in this case, I should kind of clarify that. Whenever we have a constant times a bunch of other stuff, which we can rewrite this as a constant negative 1/6 times du over u to the fourth. Whenever we have a constant times a bunch of stuff within our integral, we can pull that constant out of the integral. So doing that is actually going to give us negative 1/6 times the integral of du over u to the fourth. So now that we have this, what you also can kind of think about next, this is a little weird looking when you have a du within your fraction here like this. And this does happen, a lot of U substitution problem or integration problems in general. They may give you a problem where you have a du or a dt or a dx or whatever in your numerator. Well, really, this is the exact same thing. We can basically just move that out of the fraction and kind of tack it on to the end over here. So we can write du over here and then just replace it with a 1. So du over u to the fourth is the same as 1 over u to the fourth times du. Now, it's kind of weird because this indicator du or dx or dt, what we basically did there was we treated du as if it's its own term. It technically isn't, but within the context of, within this integral, you can kind of think of it like that. Really what it is, it's an indicator that we're integrating this with respect to u now. So now we've applied our u substitution, we've applied our substitution to this integral. And what we've done, we haven't actually integrated it yet, so we still have some more to do. But what we have done is we've rewritten the original integral we started with, this one here, and we've rewritten it in terms of u, which should hopefully give us an easier integral to evaluate. So now we can go ahead and evaluate this integral. Well, to do this, since we just have 1 over u to some power, that's probably going to be easier to rewrite this in terms of that new, well, let me rephrase that. It's going to be easier to rewrite this not as a fraction. So what you want to keep in mind is whenever you have something to a power on a denominator of a fraction, you can move it up to the numerator and make the power negative. So this is actually the same as u to the negative fourth power. So now this is the integral we're trying to evaluate. Well, the reason why that's easier is now we have this in a form where we can actually just use the power rule to evaluate it. Well, the power rule for integration just says that we're going to raise our power by 1. Well, negative 4 plus 1 is negative 3, and then divide by our new power. So this is going to be the antiderivative of u to the negative 4, which means at this point, we have actually evaluated the integral and integrated this integral. Now, when you do that, the du disappears. The du falls off because, like I said, that du was really just an indicator that we wanted to integrate with respect to u. And now that we've done that, we can get rid of the du and just have this function that is the integral of the function that we were told to integrate, or the antiderivative of the function that we were told to integrate. So now that we have actually integrated it, we want to undo our u substitution because we were given some function that was a function of t. We want to end up with a function of t. We don't want to change it to u because really in the context of this problem, the u doesn't actually have any meaning. We want to keep our variable the same. So what we want to do now is make this kind of reverse substitution where we're replacing u with 1 minus 6t instead of the other way that we did before. So u is going to be 1 minus 6t to the negative third power over negative 3. and then times -1/6. Then really at this point, we just need to kind of simplify. So the -1/6 and the -3 on the denominator, basically that's just going to be like 1/18. And then this 1 minus 6t to the -3rd would be the same as putting 1 minus 6t to the +3rd on the denominator. So basically we're going to end up with 1/18 times 1 minus 6t all to the 3rd power. And that's going to be and then I should say, actually, we need one more piece here. We do need to add on a plus c. So this plus c now is going to give us the indefinite integral to this function that we originally started with based on this substitution that they gave us. All right, so that's it for that problem. I'm not seeing any questions in the live chat here, so we'll go ahead and go on to the next example I have for you. So this time I'm going to talk a bit more about how to figure out what substitution to actually make, because like I said, that is half the challenge in these U-substitution problems. So we're going to evaluate the indefinite integral we're going to take the integral of z squared over z cubed plus 1 dz. So when we're evaluating an integral with U-substitution, like I said, the first thing we want to do is figure out what substitution to make. And I'm going to kind of split this this problem into two separate portions here. So first, I'm going to talk about what substitution you actually want to make, or kind of what the thought process looks like as you're trying to figure out what you want to make your U. And then I'm going to show you how to actually apply that substitution and then integrate the problem. So that's the question, is how do we figure out what U we want to use here? Or in other words, what do we want to say U equals in terms of Z in order to be able to do this substitution, or to be able to evaluate this integral using U-substitution? Well, the number one trick that you want to kind of keep in mind when you're trying to figure out what to make your U is you generally want to look for something, some portion of this equation here, where that thing's derivative is also in the integral. So what I mean by that is we can kind of, there's really only so many options when you're looking at a function that you're trying to integrate. And we can kind of break it up piece by piece, think about, what different things we could do. You generally don't ever want to say U equals Z, or U equals X, or U equals T, or whatever your variable is, because this isn't really going to change the situation for you at all. You're just going to put it in terms of a different letter, but it doesn't actually change the integration that you have to do. So that's generally not going to be a good idea. In this case specifically, we have a couple other options. We could maybe say U equals Z squared, maybe U equals Z cubed, this piece here, or maybe this entire denominator, Z cubed plus 1. These are kind of the, most obvious, first guesses, I guess you could say. The only really other thing would be maybe U equals Z squared over Z cubed plus 1. But of course, the issue with this is we've essentially made U everything that is in the entire integral, which is also generally not a good idea, because it's not going to be possible to make the kind of substitution for dz that we're going to have to make. It's kind of the opposite problem of what we get by making U just be Z, is instead of there not being enough change, we've basically eliminated the entire thing. It doesn't really work. So these two options are usually not going to be a good strategy. We're not just going to say U equals Z or U equals the entire function. So probably one of these in-between options is what we want to go with, where we're making U just a small portion of the actual function that we started with. So obviously, we need to figure out which one is actually going to help us get to our answer. Well, like I said, you want to think about which of these things has that thing's derivative also somewhere else in your function. So the next kind of obvious thing to think about is, what is the derivative of each of these three things? So first of all, the derivative of Z squared we could find using the power rule would just be 2z. The derivative of z cubed would be 3z squared. And the derivative of z cubed plus 1 also would be 3z squared because the derivative of a constant is 0. So basically, these two options here and here, the derivative is the same. So these pretty much are, they're going to be equivalent in terms of substituting our dz and dealing with the derivative. But based on the fact that their derivative is exactly the same, this option is probably going to be better than this option because we can kind of eliminate more stuff and still end up with the same exact derivative. So we're, probably based on that, we're not going to want to do u equals z cubed. Instead, we would prefer u equals z cubed plus 1. But let's think about really this option here and this option here. So you can see if we say u equals z squared, the derivative is 2z. We don't have a 2z anywhere in here, and it's okay if it differs by a constant. So what that means is if we had a 4z or just a z or a 10z, really any constant times z, the important thing is this z term here, that might be able to work. The problem is if we say our u is this z squared term here, what we still have is a z cubed plus 1. So this single z, or this z times a constant, is probably not going to be able to cancel out very nicely with a z cubed plus 1. So that's probably not going to be the best option. If we look at the other choice we're considering here, though, this 3z squared, we do see that we have a z squared up here, right? So if we make our u this whole denominator, the derivative of this whole denominator is the entire numerator times a constant. Like I said, it's fine if it differs by a constant, because when you're evaluating integrals, if you have a constant times something, you can pull the constant out. So that's not really going to cause us too many problems. What's important is that we have a z squared on our numerator here, and our derivative is just z squared times a constant. So this, just based on that fact right there, is probably going to be our best bet. We're going to want to say u equals z cubed plus 1. So we'll say u equals z cubed plus 1. So let's let me clean up this little section here real quick. All right. Okay, so how to proceed from here is the question. So this is kind of the second half. Now that we've decided what we want to make our u, we can actually go about applying this substitution and integrating to figure out what the integral actually is. So like we did in the last example, once we figure out what our u is, what we want to do then is figure out du, which is just going to be the derivative of u. So the derivative of this thing. Well, like we already figured out, the derivative of z cubed plus 1, we can just use the power rule. It's going to be 3z squared, and the derivative of the 1 is 0. So it's just going to be 3z squared. So then what we also need to do is put on a dz here. So whenever you do this step here where you go from u to du, you want to tack on a d of whatever your variable is. In this case, our variable is z. We'll put on a dz there. It may be dx or dt or whatever the case is. So now we can take this equation, the du equation, and solve for dz, because dz is going to be the thing that we're going to need to substitute in there. Well, to do that, we just have to divide both sides by 3z squared. And we would just get dz equals du over 3z squared. Okay, so now what we want to do is we want to take these two pieces here, what u equals and what dz equals, and just plug those into this function over here. So we can see on our denominator here, we have this z cubed plus 1, which is the entire u. So we can just replace our denominator with u. And then we have this dz here, which we know is equal to du over 3z squared. So we can replace dz with du over 3z squared. Now we still have a z squared on the numerator, and there isn't going to be a nice way that we can figure out what dz, or I'm sorry, there isn't going to be a nice way that we can figure out what z squared is in terms of u. So what we want to kind of think about is, well, that might be okay, is what I'm getting at, depending on how this is going to simplify based on our dz term. And we can see, since we have a z squared on the numerator here times this other fraction with a z squared on the denominator, those z's actually will cancel out. So what we actually have here is the integral of du over 3u, which really is the same as 1 over 3u times du. So really, this is the function that we're integrating. We're going to integrate with respect to u of 1 over 3u. Well, to do that, first of all, what we want to do is we can pull out this constant 1/3, and we're just integrating 1 over u with respect to u now, which is a fairly straightforward integral. And this is actually one of the integrals on my integral calculus cheat sheet, or my calculus 2 study guide. If you haven't checked that out yet, there is a link down in the description where you can get more info on that, and in the pinned comment below as well. But the integral of 1 over u is natural log of u. So this integral here is just ln of u. We still have our constant 1/3 out front, and then we also do want to add in a plus c. And now the thing that we still need to do, there is a little bit more to do here, because what we've done is we've just integrated with respect to u. We've basically just converted this problem into some new variable, which we just made up, right? The original function was in terms of z. We basically just made up a new variable u and plugged it in there and integrated, which is great because it made the integration a lot easier. However, 1/3 ln of u plus c makes absolutely no sense in terms of the original problem we were given that only had z's in it. The u we just kind of artificially put in there to make our integration easier. So what we need to do now is undo that, or reverse that process, which basically just means that we want to go back to the original u that we decided and plug that back into the function that we've ended up with now. So we need to replace anywhere we see a u with z cubed plus 1. So if we go back here, we want to replace our u with z cubed plus 1. And now this is going to be the integral of the original function that we were trying to find the antiderivative of. So I hope you found that helpful. If you did, please be sure to hit that like button down below. It's a huge help to me and my channel, so I can keep making more videos like this. We can keep growing the Jake's Math Lessons community and helping more people get good grades in calculus. Just not seeing any questions in the chat. If anybody does have any, feel free to drop them in there, but otherwise we'll go ahead and wrap things up here. Yeah, thanks for joining. Hope to see you next week. We'll be doing these live streams every Monday night, 5 Pacific. I do start a couple minutes late sometimes, but 5 Pacific is the goal. So be sure to subscribe and hit that bell icon so you're notified when I'm going live each week, and hope to see you there next time. Thanks.